So, okay. So last time we discussed about some of the major components of the whole structure of antenna, which, as we said, it included the source, it included a transmission line, or a line which transmitted the disturbance of the signal we want to make up, including also the signal that we want to transmit, including the specific frequency, the specific bandwidth. So we talked about the transmission line, and then we talked about the antenna itself. Now, so last time we just discussed about this whole system, but today we are going to talk about the fundamental parameters of the antenna and the properties that we can use to characterize them and to classify them. So we want to talk about the radiation patterns, the radiation power density, radiation intensity, the beam width, which is another important parameter, the directivity, numerical techniques we can use, antenna efficiency, gain, beam efficiency, bandwidth. Actually, you can go over the list. I don't need to read all of them one by one. Polarization, input impedance. This is an important parameter, which, as we said the last time, in order not to lose information or power as we are transmitting a certain signal, we want the impedance to have specific value. Then we'll talk about the antenna radiation efficiency, antenna effective length, equivalent areas, maximum directivity, maximum effective area. This 2.16, which talks about the maximum directivity, it has to do with directivity in principle with this 2.6, which is the, how can I say it, where it defines the major directions where a signal is emitted from an antenna, or the direction which we can reach, or the direction from where we can receive a signal, okay? Because we have antennas that transmit, antennas that receive, and this directivity, it just denotes the point in space where we can pick up the signal. We'll talk then about the transmission equations, the radar range equation, and as you can see, another topic that will close the list is antenna temperature. Now, to describe the performance of an antenna, we need to define several parameters. Some of these parameters can be used also to measure the performance of an antenna. Now, we know that we have three orthogonal coordinate system. You already know this one very well. I mean, you have taken the courses for this. There is a Cartesian coordinate system, the cylindrical, and the spherical coordinate system. Now, we are going to use actually, in the radiation zone or in the far zone, the spherical coordinate system is the most appropriate, okay? Because the intensity of the antenna or the power that we can measure at any point, it is independent of the angle, which means that if we are at some respective point, we are so far from the source that the intensity, it will depend mainly on the radius. That is why the spherical coordinate system is the most appropriate. Now, in the most general sense, we always make approximations, because if we do an expansion of the power of the antenna, most probably we have some nonlinear terms which make the numbers that we measure being really approximates and not exact or precise values. Actually, we know this one, and the simplest and probably the closest inequivalence between this principle and what we have seen in the past, it has been, for example, the dipole. A dipole, it's well, you know what it is. It's a plus charge and a negative charge allocated at the distance d, and that dipole, it has an electric field and a potential at some specific point. But that dipole, we can expand it in further orders and we can receive a quadrupole or octopole from a single dipole, meaning that whatever we do calculate, we have the lowest orders, which have high power, and also we have some subsequent higher orders, which have lower power. But we are going to discuss these later. What is essential for the moment is that the spherical coordinate system is the most appropriate one. And as a reminder, the spherical coordinate system, they are going to be described like this. We have here AR, capital R, AR plus A theta, plus A phi. So these are the coordinate systems, the r theta phi. The unit vectors along these three orthogonal directions, they will be AR, A theta, and A phi. So, and these here, they are the components of the projections of the field, or most of the time this would be an intensity. The projection along the AR, the projection along the angle theta, and the projection along the angle phi. And there is no need to do this one, but as a reminder, this is R, the distance from the origin 0, 0, 0. This is the angle theta with respect to the z-axis, and the projection onto the xy plane, it produces this angle phi. Okay, so, and this is the coordinate system where we have one unit of radius and two angles. Now, the first parameter that we want to talk about is the radiation pattern. Now, this is a mathematical representation of the radiation properties, and the information in the radiation pattern, it includes the amplitude, the phase, and the polarization. And this can be described as function of theta and phi. Normally, with the polarization, so amplitude is almost obvious what it is. You are going to expect an amplitude which is measured by the strength of the electric field of the electromagnetic wave which is propagating. The phase, we are going to detail this one again later. And when we talk about the polarization, we'll have the electromagnetic wave which is emitted from an antenna. It can have a specific polarization. Let's say that as this one, we can have an antenna which distributes the signal like this, and we may observe the electric field being in a certain direction, the same way that we can have a polarized wave. And a polarized, so this is E, this can be H, and as it is propagating, you might you are going to see the electric field oscillating like this, only in a single direction. Or we know how polarized light can be. This can be the electric field. If this is the polarization, we are going to see the tip of the electric the field vector is going to draw a line. If we are looking from the front, and if the wave is propagating toward you, okay? So electric field point, it can be here, 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 here. So this is the line that we could see, which makes the signal that is being emitted and received polarized. Now, the radiation properties, when we talk about radiation properties, we can talk about the power flux density, the radiation intensity, the field strength, the activity, phase, and the polarization. Now, the radiation property that concerns us is mostly the two-dimensional or three-dimensional spatial distribution of the energy that is distributed as a function of the observer's position along a path or surface of constant radius. As we said before, we said that since the most relevant coordinate system is spherical coordinate system, we may have to measure the polarization and the intensity at an outer surface which is equidistant from the original antenna. Okay, so we are assuming that at a certain distance we are measuring the same signal as a function of r. Now, We have, regarding the patterns that can be created by the antenna, we have amplitude field pattern, amplitude power pattern, and normalized field and power patterns. Now, the first one is a trace of electric, or most of the time it is going to be electric, but this is the trace of the electric field at the constant radius. Now, the second one, it does not include the electric field amplitude, but it includes the power density. We know that power density, it is something which is proportional to the magnitude of the electric field squared, okay? Because we have the E squared, it is proportional to the power. Then we have the field and power patterns. They can be normalized with respect to the maximum value. So we don't need to get all the specific values. Maybe we don't need to read the maximum value of the power, but we can normalize it to the maximum value, and we can still observe a clear distribution of the pattern of an antenna. Now, as we said, the field pattern, it can be a plot of the electric field or magnetic field as a linear scale. And the power pattern, it is going to be the square of this electric field intensity. So it's going to be like E squared. Then, a linear, this scale of the pattern of the electric field, here we have it. So, and as you can see it from here, this is the E, the magnitude of E. This is an example when we have 10 elements of an antenna, and these 10 elements, they are a quarter of wavelength far away from each other. So we're going to discuss these antennas composed of several elements in the future weeks for sure. But here we observe a pattern which we are going to commonly see or observe during the whole semester. Now, what we can observe here is there's a parameter which we are going to get used to it, which is HPBW, which is half power at the beam width. And the half power, since this is we call this half power, this is 0.5 of the maximum value. But now, since the square root of 0.5 is 0.707, that is going to, and since this one is a linear electric field, that's where we should determine where this half power is, because 0.7 squared, it is going to be 0.49 or 0.5. So we'll often worry about this distribution. We're going to talk about this distribution of the antenna in details, but from here you can see that there is a major lobe, okay, there is a major direction which has a high intensity, and we have some smaller lobes or some smaller distribution of the energy in some other direction with a narrower angular selectivity, okay? So the major lobe, it has a very low resolution in terms of angular selectivity. The smaller ones have a higher one, so the resolution is higher, which means that they are smaller, they cover a narrower angular distribution. Of course, we don't always worry about the spatial resolution, but we're just mentioning this one so that we can compare those. So it looks like the power distribution or the pattern of the power, it is going to be strongly dependent on the angular distribution or on the angle theta. Of course, with the radius, it's going to depend also, because the further we are from an antenna, the signal in principle should get weaker and weaker. That's what we expect. We don't expect the signal to get stronger for sure. Of course, also it is not going to be constant. That's also a given. So it's going to be decreasing, but rather than having only the pattern as a function of R, it is it strongly depends also on the angles. Now, this graph is the pattern of the E field. This is the E square. So this is really the power pattern. Since this is the power pattern, it is easy also to distinguish that the HP half power beam width, this is really at the 0.5 scale with respect to the maximum value. Again, this is the same distribution, the same antenna construct with 10 different elements which are equally spaced at a distance of a quarter of the wavelength with which the antenna is using. Here we are given the angle distribution, and here we have the normalized power pattern where the major lobe, or the lobe that has the maximum intensity, it is directed, well, once it is normalized, it has a maximum value equal to 1 for sure. And we see also the other lobes, once we normalize them, they look more comparable to the major lobe. Then here we can observe the polar pattern, but when we talk about the polar pattern, it looks like we can observe some other important parameters. So actually what we see here from the figure, the first one is that we have the Fresnel beam width. Fresnel beam width is FNBW. It is the angular distribution where we have the first zeros. Okay, so if we have an antenna at some space, there are some specific directions where we roughly get no signal at all. Okay, so these are called the zeros of the antenna. But the first one is what is going to define the region, the first region which has a zero reception power following the major lobe. So if we stay at an angle theta equal to 0, we have the major lobe, we can receive a very strong signal, but as we keep increasing the angle theta, so we are increasing the angle between the direction of the major lobe, we stay a little further and further, we get the zeros. After the first null beam width, we have also other zeros, which we can derive the specific values from the angular distribution of the amplitudes, okay, or of the power. Then we have the half power beam width. I think we talked about this one before. For sure, the half power beam width, it is smaller than first null beam width, and it is also easily seen from here. And this beam width, the distributions, they are measured in radians or degrees. So this is the angle, which is going to, so we'll give these numbers in radians or degrees. We have the major lobes, we have some minor lobes, and any lobe which is not a major one, they are called minor lobes. Now these minor lobes, it includes the side lobes and also the back lobes. Now the back lobe, as you can see it from the figure, it is traditionally or always on the opposite direction with respect to the major lobe. Then, so as we said, the minor lobe is any lobe except the major one. A side lobe is the radiation in any direction other than the intended lobe. And this is a good definition because once an antenna has a specific directivity, we are not very much intended in the side lobes. Of course, they send some signals, but the major objective, it is the major lobe. A back lobe is a radiation lobe whose axis makes an angle approximately pi, or 180 degree, with respect to the major beam of the antenna. Now, here we have actually the radiation intensity or the radiation distribution as a linear pattern, and here we can see the major lobes, we see the side lobes and the back lobes. The side lobes and the back lobes, they are all what we call the minor lobes. Then we can see from here the half power beam width, first null beam width, as shown in here. Now minor lobes, I think we talked about this one. The level of minor lobes is expressed as a ratio of the power density in the lobe in question, the ratio with respect to the major lobe. Okay. Side lobes, levels of 20 decibels or smaller, are not desirable in most applications. Okay. Now we want to have actually side lobes smaller than 30 decibels. We're going to discuss also later. But in order to obtain side lobes with a very low power, this requires careful design or careful construction. So, which means that we want to maximize the power distribution along the direction that we worry about. We don't, because we know that an antenna has some maximum power. Okay, so we should know this one. We don't have, and if we have a maximum power, it will be the best if this power does not distribute everywhere equally. Okay, we want to focus it, not the traditional focusing, but we want to focus it mainly in the direction that we want to communicate. For example, for the communication with radio stations, always the objective is to have the signal to push it as far as possible, meaning we want to send it to another city. So you want to have an antenna that you want to send a signal to Girocastra or Saranda, and for this one you have to have a very high current at the source, so that you can have a very high power distributed. But if you know where you want to send this, it is best that this maximum power that you can produce with a given parameters to orient it as much as possible. If you want to send a signal to Corcha, you better build another antenna which is now focused, which has a specific directivity. Okay, so here we show the normalized, the three-dimensional amplitude field pattern for a same construct of an antenna with 10 different elements with the same distance between each other, having a quarter of a wavelength. Okay, we see that in this case we have a side lobe which has an intensity of 9 decibels in the far field. Okay, and okay, so what we want also to learn from this slide is that the electric field that is going to give a measure of the power of the signal, which is distributed everywhere. The electric field, it has three components. It has the projection along the ER, the projection along the E theta, and E phi. So E theta, you can imagine now that it is in the direction as we are increasing the angle theta with respect to the z-axis. So you can see the angle theta here in the slide, and imagine for a moment that you want to increase the angle theta. In the direction of the increase, that's where we have the E theta. So it is a vector which extends, let's say, from Shkodra to Vlora. That is E theta, okay? And E phi, it is a vector, assuming now that we have the source of the antenna at the center of Earth, and E phi, it is a vector which extends from Vlora to Corcha. But it says here that in the far field, the radian ER component for all antennas should be equal to 0. So we should have no projection along the tangent with respect to a large sphere. Now, here we have some slides that we can talk about how we can generate the patterns of the antennas using some softwares, but these we are going to talk in another day. So we are going to share together the functions with which we can draw all these beautifully looking power distributions that we see, for example, here in slide 17. We will be able to plot them ourselves. And now, when we design the distribution of an antenna, we may have to select between the option of having a polar, a semipolar, or a spherical distribution. And we can have polar two-dimensional or semi-polar in two-dimensional, but again, we are skipping this discussion for now. We may discuss this one starting from the next session. So here there is also a description of how we can run these codes. So I'm calling these slides the MATLAB slides, okay? And yeah. So here there is also some description how to run the codes, which will be shared in the Google Classroom material. And now let's talk about the other parameters of an antenna, which in this case we want to talk about the amplitude radiation pattern. Now the radiation pattern, it can be isotropic, directional, omnidirectional. We're going to talk also about the principal patterns and the pattern lobes. Now The principal electric field, in this case, we show a horn antenna, and as you can see from here, the principal E-plane, the plane where we can find the electric field, apparently we have a polarized signal, because we have the E field, it is in the XZ plane. X is pointing in the direction of the propagation of the wave, and Z is orthogonal with respect to the output of the horn antenna. Or you can see it's in the red color, and the magnetic field intensity of the electromagnetic wave, it's shown here in green, and it is propagating in the plane YX or XY plane. Okay, now an isotropic radiator, it's a lossless antenna that has equal radiation in all directions. Okay, so this is an isotropic. And a directional antenna, it can radiate or receive electromagnetic waves in some well-designed directions. When we say well-designed, directions that can be easily determined by the construction or by the way that we put together the components of an antenna. Now, and we have like a reference antenna type, which is called something like a half-wave dipole. And half-wave dipole, it has, we're going to do this one again later, it has this specific pattern distribution of the signal. And it's like, and we can use it as a comparison. The moment that we can direct the power out of an antenna with a higher selectivity, or then we call this one, we call these directional antenna. Okay, so it's going to be something which is really, it's to some degree, it is really selective, or we can really make it to possible to send a signal along a specific direction. Okay, so here, actually, in this slide, we talked about we talked here about the isotropic or omnidirectional pattern. Now, omnidirectional pattern, this is an example of what this is, and we can see that for this omnidirectional pattern, we said that in the far field, there will be in the future slide actually what we mean with the far field, because the antennas actually, I remember when I was a student, one of the things it was stuck to my mind, it was that the far field, it's called the radiation zone. And the radiation zone, at least for a student of my age, it was considered like the danger zone in terms of creating unexpected effects. Okay, it's a radiation zone. And this radiation zone is far away from an antenna, which also brought us to the discussion as we were discussing in the class. Oh, okay, if the radiation zone is far away from the antenna, so let's say you have an antenna right here, but the radiation zone is considered to be very far away. And we considered it as a danger zone, if there is something, if there is one. And which also make us think for a long time, until we learn something more about the antennas, whether being close to an antenna, is it really dangerous or not? And we were thinking, okay, so if we are very close to an antenna, we are not in the radiation zone, so we are safe. So it's better to be very close to an antenna than far away. Okay, so these are some concepts which you as students you can discuss these, also based on the intuition that you might have, which should also be based very soon with good support, not only terminology. But now, here, and as we are discussing about these, we mentioned also this is omnidirectional antenna, and we are in the far away, the projection far away from the source, the projection of the E field along the ER is 0. We're assuming that E theta, it has electric field, it has a projection only tangent to this donut-shaped distribution. So if you consider this one like a donut-shaped distribution, the E theta, it is tangent, pointing along the direction where theta is increasing. The magnetic field, it is pointing again in the direction tangent to this donut-shaped power distribution with an angle A phi. Now, actually, we call this one omnidirectional, but it's not purely omnidirectional, because we see that we have, it is, because omnidirectional, it would be a direction where we would get a strong electric field also along the direction, along the z-axis, which means that where the x and y would be equal to 0. This we're going to discuss again this later. So principal patterns for linearly polarized antennas. Performance is described in terms of the principal E and H plane patterns. When we saw the horn antenna before a couple of slides, that was an example where the E plane was on the XZ direction, the H plane, it was on the XY direction. Now the E plane, it is the plane containing the electric field vector. The H plane is the plane containing the magnetic field vector and the direction of maximum radiation. Now this is an important slide, so you should look carefully also from the book whenever you see these discussions. So this is really something that you should remember among all of the slides. So here initially you have an antenna which is shown at the center in red color, and the capital D, it is the maximum space parameter of the antenna, of the construct. Okay, so you can measure it in meters. How long is the wire which is used to generate the signal that is going to be D, and the region very close to the antenna itself, so the closest region, which is region 1, this is considered the reactive or near field region, which has a radius of R1. Then we have the radiating near field region, which is between radius R1 and R2. And then we have the far field or Fraunhofer region, which is the farthest region from an antenna. Now, once we talk about these three regions, of course, it is very important to measure what are these distances actually for specific parameters. So it looks like it is something which is proportional to, for example, radius 1, it is proportional to D to the power 1.5, and it is proportional to lambda to the power 1 over 2, 0.5. Okay, so D to the power 1.5, which is the size of the parameter of the antenna, and the antenna, you may assume for the moment, it can have a size of, imagine for a moment, 1 meter. Okay, let that be the relative scale. It can be from 1 meter to 10 meters. It can be up to kilometers, because we can have antennas that are used for space exploration, for astrochemistry or astrophysics. These are antennas which can be distributed over a huge field. But let's consider for the moment traditional antennas that we may have seen for communication signal reception, and like an antenna. Imagine an antenna of a TV, of a television. You know what the size of those are, and you have seen also that these antennas are composed of several components, several conductive wires, which are placed with a certain structure, certain spatial distribution. So let's see that. So we can have we try to remember this slide, and we can read that reactive near field region is a portion where the reactive fields predominates. Radiating near field or Fresnel region, the region where the angular distribution is dependent on the distance from the antenna. But then we have the far field, where the angular field distribution is independent of the distance from the antenna, which means that you have a region where the field, the E theta, is constant everywhere. Okay, it's independent of the distance from the antenna. So you get a little further. Let me say it this way. So the E theta, which is going to be the projection of the electric field along the direction where the theta increases in spherical coordinate system, that value, it will not change if you get a little further. Okay, so if you have a signal which is going to the TV station signal, and you are using some antenna, you may imagine the following, that as you are going to the next Shkodelaja theater, the E field, E theta, it is going to be equal among the apartments that you can find in different blocks. You go one block further, E theta is going to be the same. Now, field region, as we said actually in the previous slide, these are the reactive near field, radiating near field, and which is also called Fresnel region, far field, the Fraunhofer region. Now, these two terms, Fresnel and Fraunhofer, these we can see these in many other fields of signal processing. And more traditionally, whenever a wave is distributed or it is spread out, it does not have to be a pure antenna. It's the way that we can describe the propagation of a wave. Okay, so if you have a point source and like a charge, and this one oscillates, there is a region where we can use the approximations of Fresnel, so you can read from different classical textbooks like about the Fresnel distribution or Fresnel approximation, and also the Fraunhofer approximations. Now, this could be one way of thinking about it, having a signal point source, and we can have the Fresnel and Fraunhofer distributions. Or you can have a plane wave. Imagine for a moment you have an antenna which is far away. It has propagated a long distance. It has become a plane wave. What you can do now, you can use a pinhole. You can get an aluminum foil. You get a needle. A spon. So you just make a small hole with a needle in this aluminum foil, and now this plane wave is going to be diffracted now. So it will be you can have a plane wave propagating in this direction. You get an aluminum foil. You make a very small hole, and now you have the radiating pattern. And in order to analyze how this radiating pattern is moving away, we can do, depending on the distance, we can use these two approximations, the Fresnel and the Fraunhofer. Fraunhofer, it is far away from the source, which this time we made up a point source from a plane wave using a layer which has a very small aperture. Now, the reactive near field here in this region, the phases of electric and magnetic fields they have a very highly reactive wave. There is a high impedance, and there is a high content of non-propagating stored energy near the antenna. So this energy is in principle somehow stored there. It is not propagating. Now, then we have also the radiating near field, and in the radiating near field, the fields are predominantly in phase with respect to each other. The fields don't display a spherical wavefront yet, because we are in the near field, and the pattern of a wave, it varies with distance. Okay, so what we mean here, if we get a picture of the fields as a function of distance, we're going to see different at the distance of 1,000 meters to 1,100 meters. And the third property of the radiating near field is that this is the region where near field measurements are made. This is the third region, which is a far field, and here we talk about the fields which exhibit spherical wavefront. So far field, it can also be mimicked with what we just draw here. And this wavefront, this is like a point source distribution, which is described by the e to the power jkr over r. And the pattern does not change with the distance. Now, electric and magnetic fields are now in phase. The wave impedance, it is real, so we don't have a factor which is going to include a phase difference just because of a propagation along a longer path. Okay, and power is predominantly real, or we have propagating energy, because actually when we talk about the power being predominantly real, we know that the power, it is related to the So we know that the average power density, we measure it using this expression. So we have the cross product of the electric field with the complex conjugate of the magnetic field, and then here we pick up only the real part. But the question is, what happens with the complex part? Okay, so we are going to discuss about this one again. It would be a good question. Okay, so that's the real, what goes on with the complex one. We are going to discuss this. Okay, so the takeoff message from the last 3 slides is this picture. Okay, and what you need to take to write down is the radius R1 and the R2. Let's move again. So now, and this is again something similar to what we saw in the previous 3 slides. So we have an antenna. It has a spatial size of capital D, which is on the very far left of this slide. Then we have the field distribution. It does not have initially from 0 to lambda, where lambda is the wavelength with which we are communicating. We see that we have no lobes, okay? So it is like a constant distribution as a function of angle theta. The moment we go in the Fresnel region, we see some lobes which are being formed, okay? So we see these lobes forming in the second region, and the critical values are where we see this d cubed over lambda square root, and then there is another pattern, not pattern, there is also another threshold or another boundary where we have the radiating region, or as it is called, the far field region. Now in the far field region, because this graph is shown as a function of distance from the antenna, we see that as you get further from antenna, we have the lobes being formed. So you can really select some directions where the intensity, it can be precisely equal to 0. Okay, so this is what this is the way of drawing how the field is going to change from reactive to the far field. Okay. Now here we can see again the power distribution as a function of the angle. So we can see here, as I think we talked about this one before, the power, it can even get equal to 0 at the first null beam width, but we don't have only the first null beam width, we have also other directions which are equal to 0. And here we see a picture of the power distribution. We are going to solve examples regarding the power distributions very soon. Now, when we do the analysis of the distribution of the power of the antenna, it's good to remember some important parameters. So first, we want to talk about the radian. So radian is just a measure of the angle. It's similar to degrees. Then the 1 radian, it is considered when the arc length it is equal to r. So we have a circle with radius r. Whenever the arc length is equal to the radius, we consider this one radian. Okay. So then, because we know that always the arc length is equal to the radius times the angle, but the angle has to be in radian. In this case, we have radius times 1 is going to be the r. And that's why the parameter is 2 pi r, because it is 2 pi is the angle times the radius. We get here 2 pi r. Now, we are used to this, but we have also stereo. So now, which is radian in space. So we said that radian was when the arc length was r, but now there is also a solid angle, or an angle which generates like in 3-dimensional space. If the angle which is going to cut out in a sphere defines an area which is equal to r squared, we consider this one steradian, okay, 1 SR. And in spherical coordinate system, we know that the dA, which is here the area, is shown here in equation 2.1. It is equal to r squared sine theta d theta d phi. Now, what is important to remember is that the volume element in spherical coordinate system, this is going to be equal to dr, okay? So let's not forget we have r theta phi. Then we have r d theta, okay? And then the other parameter, it is r sine theta, sine theta d phi. So this is the volume. I'm sure you can see the board here by pinning the camera, but this will not be available for the recording, but I think you do remember this. So this is the volume, which is measured as meter times meters times meters, we get meter cube. But for the area, which is seen by an angle that we can integrate over it, it can be described as r squared sine theta d phi, and the solid angle, it is defined as dA divided by r squared, and the solid angle, then it can also be defined as sine theta d phi. We know that in spherical coordinate system, the angle theta, it goes from 0 to pi. The other angle, phi, it is from 0 to 2 pi. So it's the same way as defining 180 degree. If we change from the North Pole to the South Pole, okay, that's an angle of 180 degree. But then going from Greenwich meridian, you go toward Egypt and you go toward China, you are changing the angle phi. You go backwards, you go to the Panama Channel, and you go in that path. Again, if you exclude the flat earthers, we can really have a 2 pi angle for phi, starting from the Greenwich meridian all around. That's angle phi from 0 to 2 pi. Now, here we can see an example where for a sphere, let me see this, of radius r, find the solid angle in steradians, or of a spherical cap on the surface of a sphere from North Pole. Well, now in order, and this is going to be, let's say, so here we are asking to find in steradians if we have an angle from 0 to 30, which means that we're going from 0 to 30. It is, imagine for a moment, a funnel. If you think about a funnel, Mendonian a funnel which has an angle of 30 degree from the z-axis coming down. So it is something like, what do we call on Earth? There is this geographical representation, which is from the parallel 60 to 90. There was a name regarding that. We did it in high school. I cannot remember it now. Situate na paraleli 60 deri në polin e veriut. Once you pass parallel of 60 degrees, there was something that I cannot remember. But you can think about that, or you can think about the funnel. And the funnel now, imagine it is composed of, if the angle from the z-axis to the edges is 30, now you have a funnel which has 60 degree, okay? The question we are being asked here is that find the angle in steradians for a funnel. Kjo hinka, sa ka të këndin këtu larg. In order to do that, you just need to integrate the solid angle as it is shown here. Actually, solid angle, it's also given by the equation 2.2. Then we will have to integrate over the angle theta from 0 to pi over 6, which is from 0 to 30, and the phi, it will be from 0 to 2 pi. So as best that we can make out a funnel. Yes, so here we have one. So this angle, it is from the center to the edges is 30. We're trying to find the solid angle in here. And we know one thing, that once we find the solid angle, which is here shown in this Greek letter here, if we multiply the solid angle with r squared, we are going to find the surface area which is going to be enclosed like this, okay? So this is going to be the distribution that we're discussing, multiplied by r squared. It will be this outer surface area. And we know the solid angle or the angle for a complete sphere, it is going to be 4 pi. If we multiply this 4 pi by r squared, we get the outer surface area of a sphere. But in this case, we don't have the whole sphere. We have only the specific funnel, which extends up to 30 degrees. If we integrate, we get an angle of 0.8 steradians. Okay, 0.8. This is how much, with what percentage of the maximum steradian is this? We can do it like this. This is 0.8, 83 actually. So this is 0.8, 83, or 84 divided by 4 pi. 4 times 3.14. This is going to be equal, 4 times 3 is 12, 0.84 divided by 12. This is approximately equal to what? This is 84 divided by 12. This is 6 or 7. It's 7, right? This is 7. So this is 7%. This is 7. 7 times 10 to the power minus 2. So it looks like if we have a funnel with an angle of 30 degrees, that covers only 7% of the insteradents of the total possible area with the same radius. Now this is if we integrate, which means that in the first case we find the exact value, which is 0.83566 steradians, or we can use an approximate method, which is going to be equal to, so we can somehow, in order to calculate this, rather than doing the integration, we can also use discrete steps. Okay, for that, if we calculate it, we find a value which is one steradian. And let's see, so this is delta theta 1 times delta theta 2. And okay. Now we can discuss then and by the way, you can also do this example in here, especially the first part. You may try to integrate from 0, the angle theta, you integrate this one from 0 to pi, and the angle phi from 0 to 2 pi. And if you do this calculation, you're going to find 4 pi steradians. Подождение 4π под интегрални тетен nga 0 në 180 dhe phin nga 0 në 360. Okay, so now we want to talk about the radiation power density and the radiation intensity. Now, here we are going to define a couple of a new, not new variable. We already know this. So we have this vector of W, which is in fact the instantaneous pointing vector. Okay, so this is the pointing vector. We have seen this before. We know that since the electric fields are time harmonic fields, and with time harmonic fields, we just assume, at least for the moment, that we have sinusoidal or cosinusoidal dependencies. And then we can say that the electric field is going to be equal to a real part of the phasor times the time propagator. Okay, so we used to, if you remember, we've taken before in electromagnetic field theory class, we used to say that we have a phasor description of the wave, and the phasor, it has the time dependency taken out. It depends only on the space parameters. If we multiply it with the propagator, which is e to the power j omega t, and we take the real part, we get the instantaneous expression. So again, W, it is a pointing vector, and the pointing vector, it has units of watt per meter square. So what you should take note here in this slide 38 is that the first quantity, W, it is measured in watt per meter square, and this is equal to volt per meter, because the electric field, it is measured in volt per meter, and the magnetic field intensity, it is ampere per meter. Now, if you like, we can have a short break, Do you have any question for what we did so far? Or we can give a short break.